Hi everyone, my name is Nikhil Koratkar. I'm the Clark and Crossan Endowed Chair at RPI, and I hold joint appointments in the Department of Mechanical, Aerospace and Nuclear Engineering at Rensselaer, and also the Department of Material Science and Engineering at Rensselaer Polytechnic Institute. Today I'm going to talk to you very briefly about some of the recent work we've been doing in the area of graphene-based gas sensing. Now, since graphene was discovered back in 2004, there has been intense interest in trying to find engineering applications of graphene. And one application that could have very high impact is its use for gas sensing applications. The basic principle behind how this works is that if you take a graphene device and you grow a graphene sheet, let's say, and you contact it electrically, you tend to p-dope the graphene. And this is certainly the case if you use gold contact pads. So because of the work function mismatch between gold and graphene, what happens is that electrons flow from graphene to the gold. So the graphene sheet is now p-doped. And when gas molecules stick to this p-doped graphene, they could either pull electrons from the graphene, and that increases the p-doping level, or they could inject charge into the graphene, which brings down the p-doping level. So based on the change in the carrier concentration, there is either an increase or a decrease in the resistance of the graphene film. And based on the change in this resistance value, you can then sense the gas. So this is the basic principle. It's very similar to what people have done in the past with carbon nanotubes. But graphene has many advantages over carbon nanotubes. The first one is that it's highly sensitive. So if you take a carbon nanotube, usually only the outer surface is exposed to the gas. But if you can open this carbon nanotube into a graphene sheet, then every atom on the graphene sheet is now exposed to the gas. Especially if it's a freestanding graphene sheet, certainly both sides are exposed to the gas. So it becomes very sensitive. In my lab, we've been able to sense various important gases like NO2 and NH3 at very low concentrations. We're talking about parts per billion, 100 parts per billion, in that range. So it's very sensitive. Also, it's very easy to work with, because if you think of a graphene sheet, it's very thin, but laterally it can be very large in size. I mean, you can grow a graphene sheet that's an inch by an inch. The sheet will have grain boundaries, but there are no physical breaks, in the sheet. So you can have these very large graphene sheets, which are very easy to work with, very easy to move, very easy to contact. And so the cost and the time it takes to assemble a device can be very low, and certainly much more scalable. So I think in terms of cost and in terms of not being very complex, graphene has a big advantage. Also, people have found that the electrical noise in graphene is very low, and that is also a huge advantage in these kind of applications. So I think in terms of finding a niche role in the market, I think if you're looking for a sensor that is very lightweight, very compact, that's wearable, that's stretchable, that you can carry with you into the field, that's low power, that can be battery operated, that works at room temperature, atmospheric pressure, then a graphene-based gas sensor makes a lot of sense. If you just want something that's highly sensitive, you can always use a mass spectrometer. But the problem with the mass spectrometer is that it requires high vacuum, it requires high power, and it's not something you can take into the field. It's very bulky and very complex. So if you're looking for these lightweight, compact, wearable, stretchable sensors that work in the field, then the graphene-based devices make a lot of sense. But the main issue is, can you bring the cost down? Because there are sensors out there that do this. The question is, if for graphene to replace these sensors, you've got to be able to bring the cost down. And I think that is quite possible, because unlike carbon nanotubes, which don't exist in nature, I mean, you have to assemble carbon nanotubes atom by atom and build them up. But graphene already exists in graphite. So if one could exfoliate graphite, one could, in theory, manufacture large quantities of graphene sheets at low cost, and that could really bring down the cost of these kind of sensor devices. So I think it really looks feasible, and it has a lot of promise. But there are a lot of challenges that we still have to solve. And the first challenge that I think very important is making the graphene device much more specific. Graphene is affected by so many different things that you could get a very high rate of false alarms. So if you only want to sense a certain type of gas, that becomes challenging. So I think one way is to take inspiration from biosensors. If we could design some type of a capture agent and we could coat the graphene film with this capture agent. Then the capture agent could specifically bind only to the analyte that you want to sense, and that could make it much more specific. The second challenge, I think, is making graphene devices more reversible, because many gases, when they stick to the graphene surface, they tend to not dissolve very easily. So you have to heat it to high temperature in vacuum to dissolve it. And if you're operating a sensor in the field, that is very difficult to do. So again, if one could functionalize the graphene surface and lower the binding energy of gas molecules to the graphene, then then it could be much easier to dissolve them. For example, we could maybe use joule heating at very low temperatures and be able to dissolve these gases. So again, making it reversible is very important if you want to get many cycles of operation in the field. The third challenge that I think we have to solve is to make these graphene-based devices more reliable and repeatable, from run to run. And there the issue is, if you have a single graphene sheet, it can be affected by many extraneous factors. So there could be, local flow rates might be different. There might be some charge buildup on the graphene. There might be dust particles that land on the graphene, things like that. So one way to solve this problem is if we could assemble these graphene sheets into a macroscopic network. So for example, in my lab, we've been manufacturing these graphene foams, and the foams are much more reliable, they're much more robust. It's macroscopic in size, it's three-dimensional, it's scalable, it's highly porous. So it gives you a very averaged out effect, which is not affected by extraneous factors, by localized changes in properties. So again, this kind of macroscopic ensembles might be one way to get much more reliable and repeatable results. So again, we have to improve, make the gas sensors more specific. We have to make them more reversible and more reliable. But if we can solve these challenges and if we can keep the cost down, then I think there's a very real possibility that we can move these graphene-based devices from the lab into the real world. And I certainly hope that happens in the future. And thank you very much for your time and attention.